Hi, so today I'm reading LaserTagger, Encode, Tag, Realize, High Precision Text Editing. It's from Google Research. We propose LaserTagger, a sequence tagging approach that casts text generation as a text editing task. Target texts are reconstructed from inputs using three main edit operations: keeping a token, deleting it, editing a phrase before the token. To predict edit operations, we propose a novel model which combines a BERT encoder with an autoregressive transformer model. This approach is evaluated on English text on four tasks: sentence fusion, sentence splitting, abstractive summarization, and a grammar correction. LaserTagger achieves new state-of-the-art results on three of these tasks, performs comparably to a set of strong seek-to-seek baselines with a large number of training examples, and outperforms them when the number of examples is limited. Furthermore, we show that the inference time tagging can be more than 2 orders of magnitude faster than a comparable seek-to-seek models, making it more attractive for running in a live environment. Introduction. Neural seek-to-seek models provide a powerful framework for learning translate source text into the target texts. Since their first application to the machine translation (MT) in 2014, they have become de facto approach for virtually every tasks. Translation tasks, including the summarization 2017, image captioning 2015, textile transfer 18 and 19, and grammatical error correction 2018 and 19. We observed that in some tasks generation, such as recently introduced sentence splitting, sentence fusion tasks, output text highly overlaps with input. In this setting, learning a seek-to-seek model to generate output text from scratch seems intuitively wasteful. Copy mechanism 2016 and 17 allow for choosing between copying source tokens and generating arbitrary tokens. But although such a hybrid model helps with out-of-the-vocabulary words, they still require large training sets, and they depend on output vocabularies as large as those used by the standard seek-to-seek approaches. In contrast, we propose learning a text editing model that applies a set of edit operations on the input to reconstruct the output. We show that it is often enough to use a relatively small set of output text representing the text deletion, rephrasing, and word reordering to be able to reproduce a large percentage of the targets in the training data. This results in a learning problem with much smaller vocabulary size and the output length fixed to the number of words in the source text. This in turn greatly reduces the number of training examples required to train accurate models, which is particularly important in applications where only a small number of human labeled data is available. Our training approach, LaserTagger, consists of three steps. First, Encode builds a representation of the input sequence. 2. Tag assigns edit tags from pre-computed output vocabulary to the input tokens. 3. Realize applies a simple set of rules to convert tags into the output text tokens. An experimental evaluation of LaserTagger on 4 different text generation tasks showed that it yields comparable results to seek-to-seek models when we have tens of thousands of training examples, and clearly outperforms them when number of examples is smaller. Our contributions are following. We demonstrate that many text generation tasks with overlapping inputs and outputs can be effectively treated as a text editing tasks. We propose a LaserTagger, a sequence tagging model for text editing, together with a method for generating the tag vocabulary from the training data. We describe the two versions of the tagging model: LaserTagger, a tagger based on BERT, and LaserTagger, a novel tagging model combining the BERT encoder with autoregressive transformer decoder, which further improves the result over the BERT tagger. We evaluate the LaserTagger against the strong seek-to-seek baseline model based on the BERT architecture. Our baseline models outperform previously reported state-of-the-art results on 2 tasks. We demonstrate that the LaserTagger achieves the state-of-the-art or comparable results on out of the 4 examined tasks, on 3 out of 4 examining tasks. LaserTagger is up to 100 times faster at inference time with performance comparable to the state-of-the-art seek-to-seek models. Furthermore, both models require much less training data compared to seek-to-seek models and are more controllable and interpretable than the seek-to-seek models due to a small vocabulary of edit operations. They are less prone to typical seek-to-seek models such as hallucinations. The code will be available at lasertag.page.link/code. Okay, related work. Recent work difficulties of learning neural encoders for text generation. Conventional seek-to-seek approaches require large amounts of training data, are hard to control and to constrain to desirable outputs. At the same time, many NLP tasks that appear to be fully fledged text generation tasks are natural testbeds for simpler methods. In this section, we briefly review some of these tasks. Text simplification is a paraphrasing task that is known to benefit from modeling edit operations. A simple instance of these types are sentence progression systems that apply a drop operation at token phrase level. And 2008 and 15, while more intricate systems also apply splitting, ordering, and lexical substitution. Simplification has also been a bit attempted with systems developed for phrase-based machine translation, as well as with neural encoder-decoder models. Independent of this work, Dong et al. 2019 recently proposed a text editing model similar to ours for text simplification. The main differences to our work are they introduce an interpreter module which acts as a language model for the so far realized texts, and 2. They generate edit tokens one by one from a full vocabulary rather than from an optimized set of frequently edited phrases. The latter allows their model to generate more diverse output, but it may negatively affect the inference time, precision, and the data efficiency of their model. Another recent model similar to ours is called Levenstein Transformer in 2019, which does text editing by performing sequence deletion and insertion actions. Single document summarization is a task that requires system to shorten text in a meaning-preserving way. Is being approached with deletion-based methods on token level and sentence level. Other papers have used neural encoder-decoder methods to abstractive summarization, which allows edits beyond mere deletion. This can be motivated by work of Jing and McKeown 2000, which identified a small number of fundamental high-level editing operations that are useful for producing summaries: reduction, combination, syntactic transformation, lexical paraphrasing, generalization, specification, and reordering. In 2017, extended a neural decoder model with a copy mechanism to allow the model to more easily reproduce input tokens during generation. Out of available summarization datasets, we find the one by Tanova in 2016 particularly interesting because, first, it especially targets abstractive summarization systems. 2. The lengths of the text in the dataset, short paragraphs, seem to be well suited for text editing. And 3. An analysis showed that the dataset covers many different summarization operations. Grammar error correction. In 2013-14, a system is presented with input text written usually by a language learner, and it is tasked with detecting and fixing grammatical and other mistakes. Approaches to this task often incorporate task-specific knowledge, for example, by designing classifiers for specific error types. 2014, that can be trained without manually labeled data, or by adopting statistical machine translation methods. Methods for subproblem of error detection are similar in spirit to sentence compression systems in that they are implemented as word-based neural sequence labelers. 2017. Neural encoder-decoder methods are also commonly applied to the error correction task 2018 and 19, but suffer from lack of training data, which is why task-specific tricks needs to be applied 2018. Text editing as a tagging problem. Our approach to text editing is to cast it into a tagging problem. Here we describe its main components. First, the tagging operations. Two, how to convert plain text training targets into tagging format, as well as three, the realization step to convert the tags into the final output text. Tagging operations. Our tagger assigns a tag to each input token. A tag is composed of two parts, base tag and a added phrase. Base tag is either keep or delete, which indicates whether to retain token in the output. The added phrase p, which can be empty, enforces that p is added before corresponding token. Additional task-specific tags can be employed too. For sentence fusion, okay, I will now start skipping through the paper. Optimizing phrase vocabulary. Problem 1. Problem 1. Given a collection of phrase texts, the set of all candidate phrases selects a phrase vocabulary of at most L phrases so that the number of covered phrase sets is maximized. A phrase set is covered if and only if theorem. Problem 1 is MP hard. Converting training targets into tags. Once phrase vocabulary is determined, we can convert the target text into our training data into tag sequences. Given the phrase vocabulary, we do not need to compute LCS, but can leverage a more efficient approach which iterates over the words in the input and gradually attempts to match them, first against the words in the target, and in case there is no match, two, against the phrases in the vocabulary. Realization. After obtaining a predicted tag sequence, we convert the text to realization step. While classic works on text generalization make distinct between planning and realization, end-to-end neural approaches typically ignore this distinction, with an exception of few works. Okay, for the basic tagging operation of skipping, deleting, adding, and realization is a straightforward process. Additionally, we adjust capitalization at sequence sentence boundaries. Serialization becomes more involved if we introduce special tags such as prominalize mentioned in section 3.1. For this tag, we would need to look up the gender of tagged entity from a knowledge base. Having a separate realization step is beneficial. Okay, I'm not getting this realization part. Converting training targets into tags. So they get the tags and then they have realization. After have predicted tag sequence, we convert it to the text. That's the realization. So so they have text sequence and they convert it to the text. Okay. Another advantage of having a separate realization step is that loss patterns can be addressed by adding specialization realized rules. For instance, one could have a rule that when applying tag delete to an entity, mention following as realizer must always delete the possessive s as well. Okay, tagging model architecture. So they use encoder, BERT transformer, decoder, BERT decoding mechanisms. Output tags are generated with a single feed forward argmax over encoded logits. This way, each output tag is predicted independently without modeling the dependencies between the tags in the sequence. Such a simple decoder demonstrates state-of-the-art was also named entity recognition task when applied to decoder. To better the model dependencies between the output and tags, we propose a more powerful autoregressive decoder. Especially, we run single-layer transformer decoder on top of BERT. At each step, decoder consuming the embedding of the previously predicted label and activation from the encoder. There are several ways in which we can communicate with the encoder through full initial layer, the sequence of encoder activations, and by directly consuming the encoder activations at the current step. In our preliminary experiments, we found that the latter option to perform better and converge faster, and it does not require learning additional encoder-decoder attention weights. Okay, experiments, baseline sentence fusion. Sentence fusion. Sentence fusion is a problem of using sentences into single coherent sentence. Okay, split comparison against baseline, impact with the says split and rephrase. Reverse task of sentence fusion is to split and rephrase tasks, which requires rewriting a long sentence into two more coherent short sentences. Well, that's quite an intriguing task. Abstractive summarization. The task of summarization is to reduce the length of the text while preserving its meaning. Grammatical error correction, to identify and fix grammatical errors in a given input text. Evaluation conclusion. We propose text editing approach to text generation tasks with high overlap between the input and output text. Compared to seq-to-seq models typically applied in this instance, our approach results a simpler sequence tagging problem with much smaller output tag vocabulary. We demonstrated that this approach has comparable performance when trained on medium to large datasets and clear outperforms a strong seq-to-seq baseline. The number of training examples is limited. Qualitative analysis of the model output suggests that the tagging approach is much less affected by the common errors of the seq-to-seq model, such as hallucination and abrupt sentence ending. We further demonstrated that tagging can speed up inference by more than 2 orders of magnitude, making it more attractive for production applications. Limitations. Arbitrary word reordering is not feasible within our approach, although limited reordering can be achieved with deletion and insertion operations, as well as a custom tags such as swap. To enable more flexible reordering, it might be possible to apply techniques developed for phrase-based machine translation. Another limitation is that our approach may not be straightforward to apply languages that are morphologically richer than English, where more sophisticated realism might need to adjust, for example, the cases of the words. In future work, we would like to experiment with more lightweight tagging architectures. Okay, so that's all for today. Hopefully see you next time.